All right, we have this concept called entropy. And entropy is a measure of how disordered a system is. Okay, how disorganized something is. The more disorganized something is, the higher its entropy. Now, I have to admit, my wife and I are not exactly neat freaks, okay? And so we're kind of messy. So that means that we have a high state of entropy in our home. But if we're having guests over, we clean up our house, we put everything away, scrub the floors, do all the dishes, put all the dishes away, pick up the clean laundry and actually put it away instead of the couch, that sort of thing, okay? Now, it took a lot of work to do that. We had to expend a lot of energy to do that, but we decreased the level of disorder and thus decreased the entropy of the room. Now, thermodynamically, we think of entropy as how randomized everything is. Now, for example, if I have a if I have some water here, and I have an ice cube that's this big thing of water, and so this is an ice cube, and this is just in water. Now, this is a fairly organized, low entropy situation. This is very organized. I mean, we have a bunch of water molecules all very neatly aligned in water crystals. This is maybe the water out here is at a higher temperature than this, I don't know, but it's organized. But if we wait a while, if we wait a long time, what's going to happen? It's going to melt. And so we're going to get, here's my dish with and it's eventually going to just look like this. And this is high entropy. Okay, and if you leave things alone, chances are that the system you're looking at is going to move from a low entropy state to a high entropy state. From very organized and everything's in its place to everything's messy. Everything's just kind of blah. Okay? Now, we have a way of actually measuring this, and we didn't talk about this earlier because it's really not part of our physics thermodynamic unit, but it is on the state standard, so I am going to teach it right now, and it's very simple, and it's very profound. Let me use this example again, but I'm going to make it a little bit more something you can relate to a little better. Okay, here's a glass of, I don't know, Diet Pepsi or something, I don't know. Okay, here's a straw in it. So now it's got ice cubes in it. And it's floating in, we'll just make it water. And it's at 0 degrees Celsius. So it's cold. I mean, it's ice water. Now out here is the environment, room temperature. And it's about 25 degrees Celsius. That's a nice, comfortable temperature. This is low entropy, meaning that this is pretty organized. I've got cold stuff over here. I've got molecules arranged in nice, neat crystals in the water. In the ice. And the water's cold. And out here are all these fast-moving molecules that have a higher temperature, and they're separated from these slow-moving. So everything's nice and orderly, relatively speaking. But if I wait a while, what happens? Later on, if I look at my glass of ice water, well, it's not ice water anymore, is it? What happened to the ice? If I wait long enough, it melted. And then the temperature increased until, what temperature does the water end up at? 25 degrees Celsius. And, I'll tell you what, to make it simpler, I want to make this as simple as possible. So let's just wait until the ice melts. So we've reached a state where the ice melts. Now what's true, the temperature doesn't change while the ice melts. So this is still at 0 degrees Celsius. But the ice has melted. And now it's going to start increasing in temperature. But while the ice melts, so that this is at a higher entropy. Now when I say high entropy, I just mean compared to this. Now it's still the same temperature, but the ice is melted now, right? So all those molecules of water that were in their nice ice crystals that were all arranged nice and neat, they're all like moving randomly throughout the water. So things are less organized, more disordered. What happened? Why did this happen? Because heat flowed into the water. I'm going to call this the water, and this is the air of the room out here. Heat flowed, let's call this Q. Heat flowed from the room, from the air into the water. Yes?
Why does the second soda cup say 0 degrees Celsius?
Okay, now what's it eventually going to end up at?
25.
It will eventually end up at 25, but I'm looking at this at the instant that the ice finished melting.
Oh.
So it hasn't had time to increase in temperature yet. So this is just ice melting. Well, we have a way of measuring entropy here, okay? And this is what you need to know for the final and the state standards. The way we measure, we have a symbol for entropy, a variable name for entropy, and we're going to call it delta S. Justin? Delta S. What does delta S mean? It means a change in entropy. We don't really worry about entropy itself. We worry about a change in entropy. A change in entropy is what matters. Okay. Now, delta S, by definition, this defines a change in entropy, is this. Everybody pay attention. This is your one shot at it. It's the heat that's transferred divided by the temperature at which that heat either leaves or enters the system. Okay? It's the heat divided. So what are the units here? Joules per. Now what's temperature measured in? And this is kind of a trick question. Well, if we have degrees Celsius, what's the temperature here? It's 0 degrees Celsius. That's not good. What happens when you divide by 0? The mathematical gods will take their vengeance upon you, all right? You can't do it. You can't divide by 0, folks. And this is why we have the Kelvin scale. Because you can't you'll never be at a temperature of 0 kelvins. It's impossible. So the units for this is joules per Kelvin. We have to measure a change in entropy by measuring our temperature in kelvins. So instead of saying that this water is at 0 degrees Celsius, well, what is 0 degrees Celsius in kelvins? Yeah, 273. So we're going to say the temperature here of the water is 273 kelvins. Now, what's the temperature of the air? Well, it's 25 plus 273, and what is that, 298? Okay. Now, this is how we define a change in entropy. And some of you are going to go on and become mechanical engineers or environmental engineers, even civil engineers, or study heating, ventilation, air conditioning, or something like that. This is going to be a big deal in the future, figuring out what happens with entropy. You're going to take, I took 2 whole classes, thermodynamics and advanced thermodynamics, and we studied the heck out of this equation and all that it meant. But in here, we're just kind of introducing it to you, okay? But I do want you to know this is very important. Now, 2 things got their entropy changed. The air got its entropy changed, and the water got its entropy changed. So we're going to look at both those changes now. Okay, and let's see, I want to make room here. So for the air, let me bring this up here. I'm going to go the entropy change delta S for the water. I'll go delta S sub W, and the W stands for water. Everybody with me? Okay. Now, let's just come up with let's do this with numbers because it just makes it easier to understand. Let's say that 100 joules of energy was transferred from the air into the water. Okay? So let's say Q equals 100 joules. Why at 100 joules? Because it's a nice, easy number to work with. Okay? I could have picked anything. But obviously, if you have a glass of ice water and heat is going to flow from the air into the ice water, melt the ice, at some point 100 joules will flow into that ice water, okay? So in figuring out the change in entropy of the water, I would say, okay, it would be Q over T. And I'll say, well, for the water, 100 joules was added to the water. Added. So I'm adding it, so it's going to be positive. So this is going to be adding 100 joules. And I'm going to divide that by the temperature. Now, what is the temperature of the water? And this is why I'm only looking at it while the water's melting. If you're looking at this while the water is increasing in temperature, you got to use calculus, and we're not going to use calculus in here. Okay, you'll get that if you study it in college. The temperature is, well, don't use 0 degrees Celsius. What do we use? Kelvins, which is 273 kelvins. So we increased the entropy of the water by 100 divided by 273. Well, 100 divided by 273 equals 0.3663. And what units? Joules per Kelvin. So we increase the entropy of the water by 0.3663 joules. Now this is based on this definition of what entropy is, or what a change in entropy is. Now let's do the same thing for the air. Okay? Let's do the same calculation for the air. Change in entropy based on this definition for the air. I'll use A for air. Q over T. But what's true about the energy or the heat transferred from the air? It lost 100 joules, right? The air in the environment lost 100 joules of energy. Negative 100 joules. It lost 100 joules of energy. Now, where did that energy go? It went into the water, Okay, and that's why this is positive 100. So we conserved energy there. We didn't lose any energy. It just transferred from the air into the water. And when I say the air, the room. Now, by the way, did the temperature of the air drop? Well, maybe a little tiny bit. But think about this. Did anybody bring in a cup of ice water in class right now? Oh yeah, let's say you go to lunch. Okay, you buy an iced drink like Diet Pepsi or something, and then you bring it to your 6th period class. Now, obviously, the ice is going to melt, and then after the ice is done melting, it's going to increase until it's room temperature, right? Is it going to cool down the room? By 100 joules, but you're not going to feel any temperature change. Why? Because the room has so much thermal energy to give that it doesn't even notice that it lost 100 joules of thermal energy. Also, there's thermal energy entering this room right now through the heating and air conditioning system, the sunlight through the windows, the warm air outside, bringing heat in. So this doesn't really change. This 25 degrees Celsius of the room temperature doesn't really change. So it's going to stay at 298 kelvins. So now, what is this change in entropy based on this definition? Well, 100 divided by 298 equals negative 0.3356 joules per Kelvin. Now comes something really profound. Really, really profound. And it's kind of neat. And it's really kind of neat because even at this very simple level, we can reach conclusions about the whole universe. What was the total? If I add these two changes in entropy together, this is the total, I'll call it delta S sub T, for the total change in entropy due to this change in the universe. Well, what is 0.3363? 0.3363 minus 0.3356 equals, wait, I did something wrong. 0.3663, I entered it wrong, minus 0.3356 equals, I get 0.0307 joules per Kelvin. Now, what does this mean? What are we talking about here? Well, remember we said that the second law of thermodynamics says that heat always flows from from high temperature to low temperature, right? Heat always flows from high to low, right? I mean, you'll never have a situation if I here's what was my hot coffee, right? Well, my hot coffee doesn't get hotter spontaneously. What does it do spontaneously? It always gets cooler until it reaches thermal equilibrium with the environment. Heat always flows from high to low temperature. This ice water will never get colder. Okay? Unless, you're in Minnesota in the middle of winter, and then, if the outside temperature is colder, then it will continue to freeze, right? But heat always flows from high temperature to low temperature, which means that entropy always increases. Because look, here's the change in entropy of the water. It added 100 joules, but do you see that the water was at a lower temperature? So I'm dividing this heat by a lower number. When you divide by a lower number, you get a bigger answer, right? Well, this was at the expense of the heat that flowed out of the air, but the air was at a higher temperature. That's why it lost heat. That's why heat flowed into the lower temperature water. So the change in entropy the increase in entropy was greater in magnitude than the decrease in entropy for the air, which means that overall, the entropy of the universe was increased by a little bit. Okay? So, now, what do you need to know for the final and for the state standards tests? You need to understand what this equation is. Entropy is a measure of the heat that's transferred across at some temperature. Q over T. Okay? But what does it mean? Well, if you've got a system where you've got a high temperature material and a low temperature material and heat flows from high to low, if you look at the change in entropy based on this definition, the change in entropy will always be positive. We're always going to increase the entropy of our overall universe. This is really profound. The universe, the amount of entropy in the universe is always increasing. Now, here's some really profound stuff here. At what point in time was the entropy of the universe the lowest? At the moment of creation, at the Big Bang. 13.7 billion years ago, the universe began. We've got lots of evidence to support that. And the universe exploded into existence, the moment of creation. Whether you look at it theologically or scientifically or both, okay, that was our moment of lowest entropy. And the entropy has been increasing ever since. When will entropy stop increasing?
When the universe explodes.
Nope. It already exploded, sorry. The universe will stop, the entropy in the universe will stop increasing when there is no more temperature difference, when everything in the universe is at the same temperature. Now that won't happen for trillions of years. But when it does happen, that means that the universe will be very cold. There won't be any temperature differences. Nothing will change. The universe will stop. I mean, you can almost speculate that time will stop. Not something to worry about, though. Won't happen for trillions of years. So we got lots of time to enjoy our universe. But it is pretty profound stuff. Okay. Now, to your quantity chart, you need to add a couple of things. To your thermodynamic quantity chart for your outline. Well, there aren't that many equations in thermodynamics, right? We have Q equals mc delta T. That's when heat transfers to change a temperature of substance. Or you have Q equals mHV, heat of vaporization. That's the heat that's given off or absorbed when you go from a liquid to a gas or a gas to a liquid. There's M times heat of fusion. You need to know what that means. And then now we have this other equation that we've just added. Delta S equals Q over T. This is the entropy equation. Now I think that, there is one other equation, right? Kelvins equals degrees Celsius plus 273, right? Now those are the only equations that you really need for thermodynamics, right? Now for a quantity chart, what are you going to put? Well, quantity, variable, and units. Well, what do we got? We've got Q, M, C, T, and delta S. That's about it. Oh, shoot. Never mind. I put the variable instead of the name. So just switch these. I don't care. If you put the variable first and then the quantity name, I don't care. All right? So what is Q? Q is heat. And heat is measured in joules. M is mass measured in kilograms. C is specific heat capacity. Okay, fit it in. I can't fit it in. And what is it? It's joules per kilogram degrees Celsius, or Kelvin if you prefer. T is temperature, and you can measure it in degrees Celsius or Kelvin. And then what is delta S? Change in entropy. Sorry, I'm going fast, but I got to get moving here. Change in entropy, and change in entropy is measured in joules per Kelvin. Okay, so that should be part of your thermodynamics outline, is this quantity chart for thermodynamics. Again, I know some of you are creating one big quantity chart at the end of all the outlines. If you want to do that, you can. But I prefer you do this. I won't mark it off if you do, but I prefer that you make one for each particular outline. Okay? So let's zoom out and take a look at the whole thing here. Entropy is a measure of the disorder, how disorganized things are. The way we quantify entropy is to measure the heat transferred into a system divided by the temperature of that system. And really what we're measuring here is a change in entropy. How much did the entropy change? That's all we really care about. And just make sure that this temperature is in kelvins. And ultimately, whatever process takes place in the universe, the second law of thermodynamics says that in any closed system, when you look at the overall, there will always be an increase in entropy. Okay, and you can decrease the entropy of something. Look, the air had its entropy decreased, didn't it? You can decrease the entropy of the air, but the increase of the entropy of the water was greater, so you have a net increase in entropy. Very profound stuff. That is all.